This is the Gaussian integral, and we're going to show today why its value is root pi. We're going to use a little bit of multivariable calculus as well as polar coordinates to do so. But first, what we consider is the square of this integral. Doing so, we would have the following. We're essentially going to have a version in terms of x and another version in terms of y. And now what we do is we combine these two integrals into a double integral, like so. So we are basically integrating the function e to the negative of the quantity x squared plus y squared over the real plane. And here we switch to polar coordinates. So x squared plus y squared becomes r squared, and dx dy becomes r times dr d theta. Don't forget about the r. That r has been the bane of many calculus students in the past. The bounds will now be from 0 to 2 pi for theta and 0 to infinity for r. And now we just rearrange the integral a bit. So we can take the integral from 0 to 2 pi of d theta, that will give us 2 pi. And then separately from that, we can take the integral from 0 to infinity of r times e to the negative r squared dr. That's an improper integral that we can solve using substitution. I won't bore you with the details, but I'll just show the steps here on the screen. We essentially just set s equal to negative r squared. And then in terms of s, we have the integral from negative infinity to 0 of 1/2 e to the s ds. And the 1/2 and 2 will cancel out, and then the integral from negative infinity to 0 of e to the s will evaluate to 1. And thus we just have pi remaining. But recall that this value is equal to the square of the Gaussian integral. So square rooting both sides, we get the Gaussian integral to be equal to square root of pi. Pretty neat, right? With that, I hope you're doing well. Make sure to hit that follow button for more math content. And as always, I'll catch y'all in the next one. Take care.